This comes out of the review preview section for Chapter 8. So to start off with, the Chapter 8 reviews some of our exponent log rules that should be hopefully old news to us from grades, well, especially grade 12 math, math 30, as well as math 10 a little bit. So this first one is right out of your book. It says 9 to the negative 7 over 2 and asks us what that equals. I know that you could punch that into even a simple calculator, but hopefully you recall that a negative exponent means you do the reciprocal of the base, that a denominator in the exponent says that's what root you're going to take, so we're going to do the square root of a ninth and raise that answer to 7. So I get 1 over 3 to the 7, and yes, 3 to the 7 is a great big number, so you could leave it as 1 over 3 to 7, but the point here is just that you understand what a negative exponent does, what a fraction exponent does. Next one I want to do is on the page facing it. It's number 3L. It says, we've got a squared b to the negative 3 over x to the negative 1, y squared, all that is being cubed, times x to the negative 2, b to the negative 1, over a to the 3 over 2, y to the 1 over 3. As nasty as it looks, that is actually a question out of a Math 10 assignment. Your first job here would be to realize everything in the first bracket is cubed, so I'm going to have a to the 6, b to the negative 9, over x to the negative 3, y to the 6. And again, I haven't done anything in the second bracket yet, just rewrite it. You could try to get a little bit further along, but you've got this. Now your exponent rules say when you multiply things with the same base, you can add their exponents, and when you subtract things with the same base, you can when you divide things with the same base, you can subtract their exponents. So, for example, here, when I look at the a's, I have a to the 6 over a to the 3 over 2. A to the 6 over a to the 3 over 2. Those are the only a's in this whole thing. So I can say, well, that's a to the 12 over 2 over a to the 3 over 2, so that I can subtract and say that's a to the 9 over 2. And that is as many a's as I have left here. Now, when I look at the b's, I have b to the minus 9 times b to the minus 1, which gives me b to the minus 10. B to the negative 10 is the end result of the b's. Now, if I look at the x's I have x to the negative 2 over x to the negative 3. Now, careful with your negatives here, but subtracting negative 2 minus negative 3 equals actually x to the 1, and I have x to the 1. Now, as far as the y's are concerned, all I have is, and sorry, I think I copied this last piece down, or this was a 1/3 here. I have y to the 6 times y to the 1/3, and all of that happens to be on the bottom. So I have to add those exponents, and I'll have y to the 18 over 3 plus 1 over 3, 19 over 3. So I could, leave that on the bottom like this. The only thing that I would say that answer probably has lacking is the fact that we have a negative exponent as part of our answer. So leave the a to the 9 over 2 on top, times x, bring the b to the 10 to the bottom, and then y to the 19 over 3. Good question, not because of its difficulty with the fractions and whatever else, but it makes you remember kind of a bunch of different levels of exponent rules. Now the next little piece of this gets into log rules, and before we even start talking about log rules, we need to remember what a log is. It's really just an inverted way of writing an exponent. So if I have log base 10 of 1,000, the answer is 3. The reason why the answer is 3 is because 10 to the 3 equals 1,000. So if I have log base 7 of 49, I know that the answer is 2, because 7 to the 2 equals 49. Now, not all logs naturally are going to give you such nice round numbers, but it is important to realize that if you have log base b of x equals y, it means that b to the y equals x, that those two expressions have the same meaning mathematically. That'll bring us to the next example.